this node is going to be 0. Okay, now let's write KCL exactly at this node. So if we write KCL, we have one current that goes here. This current is 0, and so the same current that goes from V in to this node is going to go from here to V out. Right? So let's write actually write Ohm's law here. So V in minus 0 divided by R1, it's going to be equal to this current, which is going to be 0 minus excuse me, V out divided by R2. If I simplify this, then we would have VO is equal to negative R2 divided by R1 times V in. Okay, so you see that our output voltage is basically a multiple of our input voltage. If you choose R2 and R1 carefully, then you can basically have output voltage as any coefficient of our input voltage. You can make it 3 times, 4 times bigger, as long as you keep these output voltage between VCC plus and VCC minus, right? This is called inverting amplifier, which you've seen before. Okay, so that's the first circuit I wanted to talk about. The second circuit is similar to this one. Again, we have a negative feedback. Let's call it R2 goes to R1 here. It gets grounded, and in this case V in is connected to the non-inverting pin. Here V in was connected to inverting pin, that's why it became an inverting amplifier. Let's actually write the same thing that we did here for this circuit. So again, because Vp is equal to Vn, this voltage, it's gonna be equal to Vn, right? So again, I'm gonna write KCL here. This current is almost 0. So let's just choose this direction for the current. So it means that the current that goes this way, it's gonna go this way. It doesn't matter what direction you choose for current. We just wanna basically find the relationship between VO and V in. So I'm just gonna write KCL here. Let me write this one here. So I'm gonna write again, I'm gonna write Ohm's law for this resistor here, 0, which is the voltage at this point, minus V in divided by R1 is equal to V in minus VO divided by R2. Means like the current that goes through R1 is the same current that goes through R2, because this current is 0. It's as if like we don't have this connection here. We actually do, right? But when we write the KCL, we can assume that this current is almost 0. So this is what we have. Let me simplify this. I'm just gonna factor out V in. V in times 1 over R1 plus 1 over R2 is equal to VO times 1 over R2. And if I simplify this, means that VO, it's gonna be equal to R1 plus R2 divided by R1 times V in. Or you can actually write it as 1 plus R2 divided by R1 times V in. Can you guys see the whole thing here? Yes. Okay, so this is the relationship that we have between VO and V in for non-inverting amplifier. right? So this is a positive coefficient because R1 and R2 are positive. So VO, it's gonna be a positive multiple of Vin. In inverting amplifier, it was a negative multiple of Vin. So these are inverting and non-inverting amplifier circuits that we made using an op-amp. Again, these are valid as long as we use op-amp in its linear region. What do I mean by linear region? It means something like this. If this is VO and this is delta V, which is V positive minus V negative. VO, this is the linear region, right? This part is saturated. What's this value? VCC plus. This part is also saturated. What is this value? VCC minus, right? So as long as the op-amp is not saturated, we have these relationships, and we can use this circuit or this circuit as an amplifier. So we can amplify a voltage using any of these two configurations. So these are the first two circuits I wanted you to see. The next one I wanted to show you is a subtractor that you also have seen before. For this circuit also we have a negative feedback. So again, we're gonna use the op-amp in the linear mode. Means like it's not gonna be saturated. We don't want it to be saturated. If you remember, in some circuits, we want the op-amp to be saturated. If you're using op-amp as a comparator or as a Schmidt trigger that you saw in your previous course, we made op-amp saturated, either using it as an open loop configuration or with positive feedback. But in the circuits that I'm showing you, we're using negative feedback, and if basically our input voltages are not that big, then output voltage, it's gonna be within the power supply voltages. So all the two rules that I mentioned, VP equal to Vn, and In equal to 0, those are valid. So let's see what the circuit that I want to show you is. Let's just like do this one. V2. So you see like we have a negative feedback here. And this one, V1. I'm just gonna name these resistors randomly. In other textbooks you might see different naming notation here, but doesn't matter how you call them as long as you derive the equations based on the configuration that you're using. Okay, so excuse me. So again,